Oh. Okay. So I've given your attendance link in the chat box. One of you may be in charge of that attendance link, can copy and paste in the chat box. So we will continue our discussion on tensor analysis. We have defined covariant, contravariant tensors, and also how we classified our tensor is depending on the transformation coefficient. You take the components of a certain physical quantity in one coordinate system, and you suppose you measure that same physical quantity in another coordinate system called prime coordinate system. So you write the transformation relation between the components of that physical quantity measured in unprimed and the corresponding value measured in prime coordinate system. So that transformation relation between the components, what exactly is the transformation coefficient there? And depending on that, we classify our tensors into contravariant and covariant tensor. So in a covariant tensor, the transformation coefficient involves the prime variable in denominator and primed in numerator. However, in the case of contravariant, the transformation coefficient or the partial derivatives in the transformation between the components, it involves prime coordinate variable in numerator and primed in denominator. Just 1 minute, I need to fetch water. Okay. Now, let us look at this problem that so that chronicle delta is a mixed tensor of rank 2. So mixed tensor we already know, like I defined in the previous this thing. This is a mixed tensor. Mixed tensor means it has both covariant, and contravariant in indices. Okay, so if it has both covariant and contravariant indices, this is called a mixed tensor. Now, for example, suppose I write like this. Suppose I measure, suppose I perform measurement in unprimed coordinate system measurement of certain physical quantity. Suppose I perform measurement of certain physical quantity in unprimed coordinate system, and that physical quantity has components in that unprimed coordinate system. As let's say that physical quantity has components like this: bi, jk. Here, this simply represents bijk. Here represents the components of that physical quantity measured in unprimed system. What is I here? I here, as you see, I is written as the superscript. Superscript means this is the covariant. Sorry, this is the contravariant index, and j and k are written in the subscript. So that means j and k are covariant index or indices, plural. Okay, covariant indices. So if the components of a certain physical quantity that you measure in a certain coordinate system, like the unprimed system here, if it has both covariant and contravariant indices, then this is a mixed tensor. And how many indices are here? 3 indices, right? I, j, and k. So 3 indices means it's a mixed tensor of rank 3. Mixed tensor of rank 3. Mixed tensor of rank 3. Okay. 3 indices means mixed tensor of rank 3 because it has both contravariant and covariant indices. Now, what is the transformation relation? So this is a mixed tensor. We already know it. So a mixed tensor should follow a certain particular transformation rules that we are going to write down. Now, suppose you measure the same quantity. Measure the same physical quantity. Measure the same physical quantity in another coordinate system called, denoted as prime coordinate system. Prime coordinate system. Suppose you measure in the same physical quantity in another coordinate system called prime coordinate system, and suppose the measurement results in the components such as b, alpha, beta, gamma. Yeah, suppose such measurement results in results in suppose that such measurement in prime coordinate system b prime. Okay, prime coordinate system results in the components of that physical quantity as b, alpha, beta, gamma, prime. Okay, this is prime system. So what will be the transformation relation between these this measurement? One measurement done in unprimed, another measurement done in another coordinate system, prime system. So you see that I and alpha are both contravariant tensor. So what is the transformation coefficient for this contravariant? In a contravariant, you remember that the transformation coefficient or the partial derivatives involved will be in the numerator. So del x alpha prime, and the corresponding contravariant index is I here. So del x I. All right. Here beta and gamma, beta and j are the corresponding covariant indices. They are in the subscript, the corresponding covariant indices. So you can write the transformation coefficient corresponding to this as del xj del x beta prime. All right. So similarly, you can write the transformation coefficient for gamma and k as del xk del x gamma prime. See, transformation coefficient here involves partial derivatives or direction cosines, and for contravariant index, the prime variable is the prime variable is in numerator. For covariant indices, the prime variable, that is x prime beta and x prime gamma, are in denominator. So that's it. That's how we categorize tensors. Okay, just so that you are clear with the concept. Now, see, if Chronicle delta is a mixed tensor of rank 2, it has to follow tensor transformation rule. What exactly it has to follow? Suppose you measure chronicle delta in one coordinate system. Let's say that in one unprimed coordinate system, let's say the components of chronicle delta are represented by this. Suppose you measure the same chronicle delta in another coordinate system called the prime system. Suppose the components are denoted using alpha. This is, let's say, alpha, gamma, alpha, beta. Okay. So if this chronicle delta is actually a mixed tensor of rank 2, it has to follow the transformation rule between this and this. So what exactly it has to follow? Del I, J. Okay. See, alpha and I are the contravariant indices. So that means what it has to follow is the partial derivative has to be del xi, del x alpha prime. Beta and j are the covariant indices. So the partial derivative will, oops, sorry, I write it all wrong. This is x alpha prime xi. This is for the contravariant index, right? Alpha and I. Beta and j are the covariant index, means in the covariant transformation coefficient, the prime coordinate variable is in the denominator, and the unprimed del xj is in numerator. So this is exactly what we should expect for this chronicle delta if the chronicle delta were a mixed tensor of rank 2. Rank 2 means there are two indices I and j here. Okay. A mixed tensor of rank 2. Now, so if it has to follow that, now let us write down. So let's say the chronicle delta sigma ij is a component of the chronicle delta you measure in one coordinate system. Then see, I is the contravariant index, j is the covariant index because I is in the superscript, j is in the subscript. So the transformation coefficient corresponding to I, you can write it as denominator del xi, and let's say del xk prime is coordinate variable in another prime system, del xk, and j is the covariant index, so del xj is in numerator, the corresponding contravariant, the corresponding prime coordinate variable is in denominator, del xl. So if we just write the expression like this, here you see that chronicle delta being having a property. What is the property of chronicle delta that we discussed before? It is equal to 1 if I is equal to j. It is equal to 0 if I does not equal j. Okay, chronicle delta tensor. So if I does not equal j, it is definitely 0. If I equal to j, it is 1. Okay, so chronicle delta is, this is multiplied by 1. Chronicle delta is 1 when I is equal to j. Chronicle delta is 0 when I is not equal to 0. So 0 into whatever this will be 0, right? So I equal to j means you just put j as I. Okay, you just put j as I, so del xi, del xi. So this and this, del xi, if you look at this, let me write it here. If you look at this, only when I equal to j, this is non-zero. When I is equal to, I does not equal j, it is 0. So we have to consider the situation in which I is equal to j only. So del xi and del xi cancels out. Then finally we have this. So what is this? This is xk prime is coordinate variable in one coordinate system. XL prime is coordinate variable in that prime coordinate system again. Okay, L and K are the indices only. So this is exactly is equal to chronicle delta in such coordinate system. Because if in such coordinate system, if K does not equal L, that means let's say K is 1, L is 2. So x1, if you remember, we write it as x, L is 2 means X, L is 2 means X 2 is another coordinate system Y. So X and Y are different coordinate variables. We know that del X upon del Y is 0, isn't it? So if K is 1, L is 1, then X1 is 1, X, and XL instead of XL, we write instead of XL prime, X1 prime will be X prime. So it will be del X prime, this is 1. So this partial derivatives is your chronicle delta in such prime coordinate system. So if you look at this, chronicle delta in such prime coordinate system is this, and chronicle delta in unprime coordinate system is this, and the transformation coefficients are this. So if this is a transformation coefficient, you see that the transformation coefficient clearly shows that this is a mixed tensor of prime 2. It involves two partial derivatives, and corresponding to K and I index, you have partial derivatives in which xk prime is in numerator, xi is in denominator, and like that. Okay. So now let us move on to this symmetric and antisymmetric tensor. I somehow have a hiccup.
Anh nói chuyện sao mà?
Thêm more.
Step là. À. Đây à.
In nói ảnh là nghe cái đầu ra in nói research là quả. Cái nào muốn sang tất cả cũng là dùng do trên từ. Okay. So symmetric and antisymmetric tensor. Symmetric means, I think you have studied symmetric and antisymmetric matrices also. Symmetric means when you interchange the indices of a certain quantity and the property or that quantity is not altered. So that means Aij is equal to Aji. This is called symmetric tensor. And this Ij, they are in superscript, means they are this quantity is symmetric tensor, which is a contravariant tensor of rank 2. Aij is equal to Ji. And if when you interchange the indices, if the sign of that physical quantity, if the sign of that quantity changes, like Aij is equal to minus of Aji, then this is called antisymmetric tensor. Now let us see this a very simple problem again. So that the symmetry or antisymmetry property of a tensor is invariant under coordinate transformation. So here let us consider Aij to be a symmetric, and they are in superscript, mean contravariant tensor of rank 2. Symmetric contravariant tensor of rank 2, and this is the component of such tensor. This is the component of such physical quantity measured in one coordinate system, which is unprime coordinate system. Okay, so if it is symmetric, means Aij is equal to Aji. Okay, now let A prime alpha be the same physical quantity, the components of the same physical quantity measured in another coordinate system. Components of the same physical quantity measured in another coordinate system. So it's in the prime coordinate, and alpha beta are the two contravariant indices. Alpha beta are the two contravariant indices. Then if the symmetry property of a tensor is invariant under coordinate transformation, we have to show that A prime alpha beta is equal to A prime beta, alpha. This is what we have to prove. So in the new prime coordinate variable also, this physical quantity has to maintain its symmetry property. If it is symmetric in one coordinate system, it should also be symmetric in another coordinate system. That is exactly what the statement of the problem is, right? So now you can write the transformation relating to the components in the two coordinate system, that is a prime alpha beta and aij. So alpha and I are the corresponding contravariant indices. So del x alpha prime upon del xi. Beta and j are the corresponding contravariant indices del x beta prime upon del xj. Right. So this is, I think, probably clear to you how you're writing transformation coefficient by now. If you listen to the lecture and also follow up with the material, the lecture notes. Now, yeah, if this has to be invariant, this is what we have to solve, right? Now, we can write a transformation relation for this also between this and aij. So if you write between aij and a prime beta alpha, beta and I are the corresponding contravariant indices. So you can write the transformation coefficients as del x beta prime upon del xi. Alpha and j are the corresponding contravariant indices. So del x alpha prime upon del xj. Here on the right hand side, if you look at this, I is a repeated index, j is a repeated index. So we have given you the statement of the property of dummy indices. So dummy indices can be interchanged without altering the value, right? Dummy indices can be interchanged without altering the value. So you can interchange these dummy indices I and j. So you interchange here, it becomes ji. You interchange here, xi becomes xj, xj becomes xi. So this is the statement after interchanging the dummy indices, or after recalling or employing the dummy indices property. Now, yeah, this is just a rewritten of the same line. This is after interchanging because of the dummy indices property. Now, see, we know that aij is symmetric in unprime system. So aij is equal to aji, right? So instead of aij, we simply write aji. Okay. Now, next, what you have to consider here is, say this is partial derivatives, this is partial derivatives. These are scalar quantities, right? You can just interchange the equation. You can multiply these partial derivatives with this, or you can multiply these partial derivatives with this. So interchanging the equation doesn't matter. So after interchanging the equation, this is what we get. So if you look at this expression is same as your a prime alpha beta expression. This expression is same as a prime beta alpha expression. So therefore, this quantity is a prime alpha beta. That means if you are having this property in one coordinate system, that property is maintained in another coordinate system, the prime system. A prime beta alpha is equal to a prime alpha beta. Okay, so that is simple. Now moving on. What time is it? Yeah, we still have time. Moving on. So that a symmetry property of a mixed tensor is not an invariant property. So here, let us write this as the symmetric tensor, or this is the component. This represents the components of a certain physical quantity measured in unprime coordinate system. So if it has symmetric property in such coordinate system, aij will be equal to aji without changing any sign here. So I is a superscript index or the contravariant index, j is the covariant index, and you can interchange them. J is the contravariant, I is the covariant index. So that quantity does not change. That physical quantity does not change when you interchange. That is what we call it as symmetric. Now let us assume that A prime alpha beta represents the components in another coordinate system. The prime coordinate system represents the components in the prime coordinate system. Then you can write the transformation relation as between these two as, say, alpha and I are the corresponding contravariant indices. So the transformation coefficient for those indices will be x alpha prime upon x alpha xi. Here alpha is the alpha prime is the prime coordinate index, so it's in numerator. Since this is contravariant, these are contravariant indices, and beta and j are the covariant indices, so the transformation coefficient corresponding to such beta and j coefficient is del x prime beta. So this is in denominator now, and this xj is in numerator. All right. And you can also write the transformation between x prime beta alpha and a prime beta alpha and aij. So here beta is a covariant contravariant index and I is a contravariant index corresponding to these two indices. You can have this covariant, alpha is covariant, j is covariant corresponding to these two indices. You can have this transformation coefficient. You can have this transformation coefficient. Okay. So by interchanging the indices here, see, j is repeated index, dummy index, I is repeated index, another dummy index. So you just interchange the two dummy indices. So wherever you have I, you just put j. Wherever you have j, you just put I. So xi, xj, aji. And also we know that ji is equal to aij, because we claim that this is a symmetric tensor in unprime. So aji, you write it as aij. Now if you look at this expression here with the expression for this, you find that xi here, xi is in numerator, here xi is in denominator, or xj is in numerator, xj is in denominator here. So this expression and this expression are not identical. That means a prime alpha beta does not equal a prime beta alpha. So your symmetric property, that is interchange of the indices, does not alter the quantity. So that is a symmetric property. That symmetric property is no longer maintained here, as you can see here. Okay, no longer maintained. Now this is one very simple example. If aij is antisymmetric tensor, antisymmetric means aij is equal to minus of aji. Okay. If bi is a vector, so that aij, bi, bj is equal to 0. So you just take the left hand side of the expression. Left hand side of the expression is this. Here you see that I is dummy indices. In this expression, there are two i's and there are two j's. So they are dummy indices. So you can interchange them. So interchanging the dummy indices, aij, bi, and bj equals aji, bj, and bi. So even if you interchange the indices, it does not alter the quantity. That is the property of the mean indices. So by employing the property of indices, we can clearly see that this is equal to this. All right, this is equal to this. So now if you use the antisymmetric property, that is aij is equal to minus of aji. So aji is equal to minus of aij, right? Antisymmetric. So you have this. Now you transfer this to the right hand side. If you transfer this to the right hand side, this is you have, and this is 2 times this, and 2 you divide 0 with 2, it is still 0. So this property you can prove it like this. Simple. And this we don't really need to do it. Like suppose if f is a function of f is a function of this coordinate system having n number of dimensions x1, x2, x3 to xn. And using the theorem of partial derivatives, if I have a certain quantity which is a function of more than one variable, infinitesimally small change in that certain physical quantity can be expressed like this. Change in that physical quantity with respect to one coordinate variable multiplied with small increment, small element along that coordinate variable, plus rate of change of that physical quantity with respect to another coordinate variable multiplied with small incremental change, infinitesimally change in that along that coordinate variable, dot 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 dot, and like this. So this is a summation from I equal to 1 to n here. So you just put the summation sign. And according to Einstein's summation convention, see here, there are two indices I and I here. You don't really need to put this summation sign. So you can simply write it like this. Now, again, this is also a very simple thing. In 3 dimension, so that sigma I is equal to 3. So, yeah, we already know that this Kronecker delta is a mixed tensor. Kronecker delta is a mixed tensor. We have already proved that of rank 2. Okay, so instead of writing sigma I, let me just write sigma I, 1 in the superscript, 1 in the subscript, because we know that this is a mixed tensor of rank 2. So also we know that I is at the mid index. If I is at the mid index, that means there is a summation over that index. In 3 dimensions, the summation from I for I will have to be from I equal to 1 to 3 in 3 dimensions. I equal to 1 for one dimension, I equal to 2 for another dimension, I equal to 3 for another dimension. So now you just write I equal to 1. So sigma 1, 1, sigma 2 to sigma 3, 3. You know that like in a Kronecker delta ij, this is 1 if I is equal to 1. So if I is equal to j, this is 0 if I does not equal j. So here in this case, this index is 1, this index is 1. So 1, 1 means this quantity is 1. 2, 2 means this quantity is 1. 3, 3 means this quantity is 1, because the contravariant index and the covariant index are identical in this case, right? So 1 plus 1 plus 1 is 3. So if you have 5D space, in the 5-dimensional space, the summation will have to run from I equal to 1 to 5, sigma I, and it will be sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3 plus sigma 4, 4 plus sigma 5, 5. And this is 1 plus 1 plus 1 plus 1 plus, it will be 5. All right. Now, maybe with this, we will finish. I need one more lecture probably. This problem, I will discuss this. After that, this problem, I will discuss this problem. We'll discuss this problem also. This problem. Yeah, not much. Okay, we'll finish with this. Now, if a subscript alpha beta multiplied with x alpha x beta equals 0 for all values of the variables x1, x2 to xn, so that aij plus aji is equal to 0. Aij plus aji is equal to 0. Okay, so the condition we have is this, right? The condition we have is this. Now, so let us differentiate with the coordinate variable xi. So a alpha beta, we take it as a constant with this differentiation. So x alpha, x beta, they are variables or the functions. So this will be differentiation of this function multiplied with x alpha. The second term will be differentiation of this multiplied with x beta. So you have 2 terms. After differentiating with xi, we have 2 terms, right? So it's like differentiating x alpha x beta with respect to xi. So x alpha differentiation x beta dxi plus x beta differentiation x alpha dxi. That's it. right? So you have two terms. And here in this term, this is the coordinate variable in one unprime. This is also coordinate variable in unprime. So this partial derivatives between the two coordinate variable is what we call it as, what we define it as chronicle delta sigma I, sigma beta I, and this is also the same thing, chronicle delta sigma alpha I. All right. So we know that this chronicle delta sigma beta I is equal to 1 if beta is equal to I, 0 if beta does not equal I. Okay, so we only have to consider the situation in which this is 1. So the term which is corresponding to beta does not equal to 0 is 0. Beta does not equal to I is 0, right? So that means when beta is equal to I, this quantity becomes 1. And you have to replace beta with I here, beta with I here. So a alpha I x alpha plus, similarly here, this quantity will be 0 if alpha does not equal I. It will be 1 only if alpha becomes I, if alpha is I. So ai beta x beta. All right. Now differentiating again with xj. So if you differentiate with xj, you have this term, you have this term. Again, this is your chronicle delta alpha j, chronicle delta with indices beta and j here. And this quantity will be 1 when alpha is equal to j. So therefore, this is actually your a j I. Okay. And also this quantity will be 1 when beta is j. So this quantity will result in a I j. So a alpha I plus a I j would be a I j plus a j I will be 0. So you just use the property of chronicle delta, then you can prove it. All right, so I will stop here because I'm going to have your 6th semester class, your seniors class at 10:30. So I hope everyone has put your attendance. We will need at least just one lecture probably this week. We'll see which time is convenient. I want to finish up our syllabus this week. Subsequent weeks, we will use it for, class tests and all. Okay, stop everyone. I will end the session. You can exit the meeting.